All right, we're going to look at some more net change problems. For this particular segment, we're going to look at graphs. Let's go ahead and read example 1 together. It says, a velocity of a squirrel running across a power line is given by the following graph. So keep in mind that right off the bat, this is a velocity graph. It's not a position graph. So for each y value on this graph, it gives us the velocity of the squirrel, and it's going to be in feet per second. So here's our graph. We can see that at time t equals 1, the velocity of the squirrel is 0. And then we can just pick some other y values. At t equals 2, the squirrel is going 4 feet per second. Then it remains 4 feet per second. Then the velocity decreases to the point of 0, and then it becomes negative. So actually the squirrel starts to back up on the power line. And then eventually it goes back to 0, meaning the squirrel basically turns around and the velocity becomes positive again. We're going to look at more problems like this later on in more detail, but for right now, again, we're focusing on net change problems. So let's go ahead and see what the question says. It says, how far, let's zoom in a little bit, how far is the squirrel from his starting position after 12 seconds? So I'm going to underline the word how far. How far basically means from how far from his starting position actually is the definition of displacement. Okay. Now, if we were talking about total distance traveled, that would be a completely different way of, not completely different, but we would have to use different methods to solve that. However, how far is he from the starting point after 12 seconds is a displacement question, and velocity, if you integrate velocity, you get displacement. Okay. So basically what that means is we're going to be finding the area under the curve of this graph. Since this is a velocity graph, if we integrate it, it will give us displacement. It will give us the change in position from 0 to 12. So that's exactly what we're going to do. So step 1 says, determine the signed area under the curve using geometry, or approximate the area under the curve using Riemann sums. Now, why are we doing this route? Because it's graphic. We don't have an equation, so we can't find an explicit antiderivative. In this particular case, we're going to be using geometry, and that's because the graph is so rigid. It will be easy for us to just split this up into triangles, trapezoids, and rectangles and figure it out from there. So we will be using geometry to figure out the signed area, which will give us the displacement. Signed area velocity is displacement. So let's go ahead and take a look. So first of all, we can split this first section of the graph up into a triangle. Notice that that's half of this rectangle, so 2 times 4 is 8, half of that is 4. So the area of this first shaded region is just 4, this little triangle. Okay. Next we have a rectangle, which is a 3 by 4. And obviously the area of that would be 12, 3 times 4. Alright, then we have the same exact triangle before, but going the reverse way. And again, that's half of this rectangle right here, half of 8 is 4. Or you could do the area of a triangle, either way. Alright, then we have a trapezoid right here. The area of a trapezoid is 1/2 h b1 plus b2. 1/2 times the height b1 plus b2. If you look at the first base, it's 4, the second base is 1, and the height is 2. So it's 1/2 times 2, 4 plus 1, which gives you 5 back. So the area of this trapezoid is 5. However, the caveat is it's below the x-axis. And when you're doing the integral velocity to get displacement, when you're doing net change, anything below the x-axis is considered negative. If it's total distance traveled, you would consider this positive, and that's basically where this problem differs between total distance traveled and displacement. If you think about it, it makes sense because this squirrel is, if its velocity is negative, that means it's backing up on the power line. And so eventually, when its velocity increases, basically he's backtracking here. So it's going to deduct from his displacement where he ends up. And then finally, we have this little itty bitty triangle at the end, which is just half of 1 block, so it's 0.5. And that will give us, if we zoom back out, this area will give us this displacement, or it's changing from its starting position from 0 to 12 for the squirrel. And I'm just going to circle that in pink. So we're going from 0 to 12, finding the area under this curve. So if we just add up all these individual areas that we got, including this negative one, we should get the total displacement, or just to say displacement of the squirrel. It's changed in starting position. So let's just add all those up, making sure the -5 is negative. We get 15.5. 4 plus 12 plus 4 plus -5 plus a half is 15.5. So that's step one. You're just finding the area. Again, you're either using geometry or using Riemann sums to approximate. Now step two is just to answer verbally. So what is the answer to the question? The squirrel is 15.5 feet away from its starting position. That's all the question was asking. Again, it's just asking, here's the velocity graph. We want to know how far is the squirrel from its starting position. We want to know its displacement, and we do that by finding the net area of velocity, making sure, again, to include these areas as negative. We find out that the squirrel is 15.5 feet from its starting position. Later on, we will address the question of total distance traveled, which basically the only difference is, instead of making this 5 negative, we would consider it positive, and that would give us the total distance traveled. In this case, I believe that'd be 25.5. All right, that's it for this question of integrating velocity to get displacement. To get the net change. If you have any other questions about this, let me know.